The surface of the moon and the surfaces of the terrestrial planets have all been extensively modified by extreme volcanic activity in their distant pasts. And these large eruptions are mostly unknown in the manner in which they emplaced large, vast fields of lava. But there was one place in the solar system where such voluminous, powerful, extensive flows, volcanic eruptions are taking place, and that is the Jovian moon, Io. Io holds some fascinating views of how Earth might have erupted in its distant past, is a key to understanding the evolution of the large Jovian satellites, and is a great template for looking for volcanically active exoplanets. It's truly an amazing place to a volcanologist. I think I have a pretty cool job because I study volcanoes for NASA. And although this usually means that I spend most of my time staring at a computer screen and crunching data and looking at remote sensing observations of volcanic eruptions, occasionally they let me out to go and play on a real volcano somewhere. And it's a great job, it's very exciting, and it's taken me to the ends of the Earth. So here we have the 4 large Galilean satellites as imaged by the imaging system on the Galileo spacecraft: Io, Europa, Ganymede, and Callisto. Io is closest to Jupiter, and Callisto is furthest away. And here we have Io, as seen by the camera system on the Galileo spacecraft. And the colors of Io's surface are diagnostic of composition. If it's yellow, it's rich in sulfur. White areas are rich in sulfur dioxide. But what's of great interest to me are the black areas and the red areas. The black areas are areas of silicate volcanism. This is where material like basalt is being erupted onto the surface. The red areas are thought to be short-chain sulfur allotropes, which are evidence of active or ongoing volcanic activity. So every black or red area in this image is an active or very recently active volcano. And Io gets twisted each time it passes one of the other 2 satellites. And it's this tidal flexing that generates heat within Io that manifests at the surface as active volcanism. So it's an external source driving this extraordinary level of volcanic activity on Io. It's an elegant cosmic ballet, if you like, choreographed by the immutable laws of physics. Now, just to put the majestic scale of Io's volcanism into some sort of context, this is the amount of material that is erupted from Earth's volcanoes every year. Most of this is erupted on the ocean floor at mid-ocean ridges. On Io, this is the amount of material that's erupted every year to erase any evidence of impact craters. There are no impact craters on Io, unlike any other solid body in the solar system. So there really is a truly astonishing amount of volcanic activity taking place. Over the years, we've collected a lot of data from spacecraft, and this is a mosaic compiled from the best Voyager and Galileo spacecraft data. And basically, we've covered most of Io at resolutions good enough to identify volcanoes from their appearance and their thermal emission. And to this has been added a growing data set, an astonishing library of observations obtained with large telescopes based here on Earth. This is from the Keck telescope in Hawaii. And these are telescopes equipped with adaptive optics. And this is measuring the heat from a whole series of hotspots. And so putting all of these data sets together, we've been able to catalog all of the volcanoes on Io and quantify their thermal emission. This plume deposit is a lava flow field which was emplaced between the Voyager and the Galileo missions in a period of about 16 years. So we can go in and take a closer look at this. Here we have the flows at Prometheus. And for scale, we have an image of Earth's most active basalt volcano. This is Kilauea in Hawaii. And this is the area of flows which was emplaced in about the same time. So the area of flows here is over well over 1,000 square kilometers, and it's actually over 2,000 square kilometers. It's about the area of Rhode Island, and this was emplaced in just 16 years. This is a particularly interesting volcano because what we think is happening here is that lava is coming up at a vent here and then passing through a lava tube system before erupting out at the distal ends of the flows. Very much like what we see in Hawaii. And a logical explanation is lava tube transportation of new lava, which is a great way of transporting lava a great distance without it cooling and solidifying. But along the way, we see these tantalizingly faint, small thermal sources, which could be breakouts onto the surface or skylights, which are holes in the roof of a lava tube. And I'll certainly be coming back and discussing those later. Io's most powerful volcano is in a feature called Loki Patera. And the general consensus is that this is actually a large lava lake. But it's a lava lake 180 kilometers across, so it's probably better to call it a lava sea. It is Io's most persistent, powerful volcano. And we think that it has a very unique way of being resurfaced. We think that what is happening at Loki Patera is that the crust on the lava lake forms with time, and it thickens with time until it gets to a point where the crust starts to sink. And then basically the entire surface of the lava lake is resurfaced by this crust sinking and the sinking crust being replaced with new lava. This is an analysis of a single Galileo NIMS observation that was obtained in 2001, and it shows a temperature map and age map of the surface from the analysis of the data. And what this implies is that this resurfacing wave, if you like, swept around the Patera at a rate of about 1 kilometer a day. So what happens is the Patera resurfaces itself, and then it remains quiescent for a while the crust thickens, and then the crust sinks again. And it's been doing this periodically for decades. A more active lava lake on Io is at Pele. And Pele is at the center of this bright red deposit, which is a plume deposit, a plume fallout. It's a plume that's hundreds of kilometers high, and it's led to this deposit on the surface, rich in short-chain sulfur allotropes, about 1,200 kilometers across. And we think that Pele has every appearance of an active overturning lava lake with the plume basically forcing its way up through the middle of the lake and disrupting the surface, revealing high temperature lava. And it's much larger. It's about 38 kilometers across and much larger than its terrestrial equivalents. This is the Kupainaha lava lake in Hawaii. Terrestrially, lava lakes are maybe 10 or 20 up to 100 or 200 meters in diameter. Io's volcanoes, Io's lava lakes seem to be hundreds or even thousands of kilometers, square kilometers in size. Loki Patera itself, Loki Patera has a surface area of over 21,000 square kilometers, which makes it even larger than West Virginia. Io's most powerful eruptions, thermal outbursts, are now known to be caused by large lava fountains gushing forth from long fissures. And these sort of events were actually seen. A couple of them were seen by Galileo. And this is what's happening along this fissure here. And this is the result of saturation, because so much energy was being received by the spacecraft, the detector saturated. And this is a problem that we've come across time and time again with trying to image these very powerful events. We now see these things from Earth-based telescopes. They were actually discovered by Earth-based telescopes back in the 1990s. but we're continuing to discover these. They're quite rare, and they're quite short-lived, but they're very powerful. In 2013, we saw 2 of these at Rarog and Loki Patera in the southern hemisphere of Io. This is an interesting image because it does show that at short wavelengths, that Loki Patera does not emit a lot of energy. Most of the energy being emitted from Loki is at longer wavelengths. And what that tells us is that, generally speaking, Loki is a relatively cool surface compared with what we see at these outbursts. So for the purposes of determining eruption temperature of the lava, Loki Patera may not be our best candidate, whereas something like Pele, where we have overturning lava lakes, an overturning lava lake on a much shorter time scale, is a better candidate.